PCBs. Right. So look, before I share my screen, now we have created a PCB. Sorry. We've created all the tracks and traces, connected everything up. We have our silk screen ready to go. We've created our PCB or our copper layers, everything, our copper fill layers, everything is ready. And we have our drill holes. Now, in which format do we send it to the PCB manufacturing company? Well, I've found there's about roughly three ways ways that you can send boards to be created by manufacturing company, and they will tell you which method they prefer. Now, how do I know which methods they prefer? Well, they will tell you. They will ask you, upload a file, and they will tell you usually in what software you use to upload that sort of file. So for Eagle, they'll ask you to upload the Eagle br.brd file. For KiCad, roughly the same thing, and so on and so forth. And whichever software you're using, they will ask for a certain for that file. And I'll show you what it's like. But if we as a BRD file, and I'll show you what that looks like. But also there is something called a Gerber file. I'll just write this in the chat. Standard file configuration that all PCB manufacturers accept. If you export your Gerber file, you're almost guaranteed that every single manufacturer and every single machine can be able to understand that Gerber file. A Gerber file breaks down your design according to its layers that you have created, and also produces a drill file. And then you have your first layer or your top, let's say your silk screen, then you have your resin screen, then you have your top layer, your bottom layer, and the silk screen for that, and all those layers are saved in Gerber file in a format that everybody can, or most PCB manufacturers can understand. And it's relatively easy to save your design as a Gerber file. And then the last option, which some design companies you ask for, is just a simple PDF of your top and bottom layers. That also works. But I've found that only very, very, very rarely. And most modern companies will ask you for either the design file in the format of the software you're using, or a Gerber file. So let's just have a look at those two options. So right, I can save this. I save this, and let's also save it as something else. So I'll just create a new folder, and I'll write this, or name it exports. And in exports, I can save my file, and you'll see that I can save it as a .brd file. And this is the file configuration for Eagle, and it saves this configuration. So the next element that I can save it as is the Gerber file. So I can export it. No, not export it here. Yes. So what I've clicked on, excuse me, I can click on CAM, C-A-M processor. Click on CAM. It opens up this element here. So here you'll see my output files. I have it as Gerber, and here I can choose the Gerber file type. Usually, the company will also designate which Gerber file format they would like you to save it as. But it doesn't. Usually, the default one, the Gerber RS274X, is the default version file. And you can see here are my different Gerber files, my top copper, bottom copper, my profile, which is the outline, my solder mask at the top, solder mask at the bottom, solder paste bottom, top, and paste bottom. Wow, that's very interesting. And we do not have that for our components because we do not use SMD components. So the solder base top and solder base bottom only comes into effect if we're using surface mount components. And how that works is that you can have the manufacturing company also place solder paste on the surface mount pads if you have SMD components. And we'll do a design with SMD components now, and we'll see how that works. So then you order your board, and it comes already with everything made, and also the solder pads, the SMD pads, already have the solder paste attached. So you only insert your component, use a heat gun to melt the solder paste, and your component, your SMD component, then sinks into solder paste. So you can have a Gerber file which designates the area or the locations where the company can put solder paste for you. Or if you have a machine that assembles your board for you, you also need the solder paste layer. And then obviously the silkscreen top, silkscreen bottom is the names. And here also on the layers, it tells you which layers it is exporting to this, to my Gerber file. And we also have a drill file. So this is all my Gerber files. I can click on process job, and it generates all of my Gerber files here. So let's go to my projects. In my export folder, I select that folder, and it processes all of my CAM data in that folder. So I can open the folder again. It opens the folder. And here we can have, here is my .brd file. And you can see it's an Eagle board file. And here I have got the folder for my CAM outputs. There I have my assembly, my drill files, and also my Gerber files with all of my copper bottom, copper top, profile, silkscreen, solder mask, solder paste, and so on and so forth. So all my files exported as Gerber files. Now you get, you also have the opportunity to ensure that your Gerber files are correct. Usually you go to a website, I just search for an online Gerber viewer. You can choose any one you want. Usually PCB manufacturing companies, there's this PCB company called PCBWay. Let's just choose this one. And we can upload Gerber files Gerber files, export, CAM outputs, Gerber files. We can select all of them and open. And here we can see all of our Gerber file as a PCB board. We can have the top layer. We can have a look at the bottom layer. And also we can hide different layers if we so like. So that is Gerber files. So manufacturing company or the process they use, they will ask you for the PCB in a format that they can understand. More often than not, they will ask for your Gerber files, which we have just exported as CAM, as CAM outputs. Those Gerber files we can then send to the company, and just as we've just generated in the online viewer, that is what your Gerber files should look like. And the Gerber files saves, so like every single layer that you have created as a separate Gerber file, and then the manufacturing company then just loads all of those files, lays them over on top of each other, and then uses those information to feed into their machines, creating your PCB. Now, as well, they might also ask you for the PBRD file, which is just the saved file from your schematic. So if we switch from schematic to the board, if you save that board, then that is the board file, and some companies will ask you for that file. So it depends on which manufacturing company you are working with. It depends on which what they ask you to do, but usually it'll be a Gerber file. If you create a Gerber file, then usually that is fine. That's the correct file that most machines can understand or interpret. Okay, so now we are going to be looking at a more advanced project. Not advanced. We're going to be slowly building up the complexity of our designs, and also adding in some SMD components. We'll see how much of our design we can create with SMD components and see what that looks like. Okay, so I looked at the internet just for some designs that I would like to follow, some little projects, and I found this website. Let's just open it up and this website is called Build Electronics Circuits. So I'm just going to add this into the chat. And from this, they have a couple of tutorials on circuits that you can create. And one circuit that I liked, or that I would like to have tried, is this Knight Rider circuit. So what does this look like? Well, it basically just has these running lights. So it's just a normal circuit with a bunch of resistors, a capacitor, an IC, and a couple of LEDs. And all it does is it's just got these little running lights connected to a battery, and that's all it does. So I decided, right, I would like to build this product, but I don't want to use a breadboard like they have done. I want to create my own PCB, and then from there we can have a cool little project. So let me just have a sorry, I just received an email of somebody not receiving the links. I'm just going to send this link just quickly so that right. layout. Sorry, I'm just seeing that I've received an email with some students that did not receive the link. I just sent the link again, just for everybody to make sure that everybody can join. But anyways, let's continue on. So, right. So I went to this website, I found a project that I would like to have built, and we're going to be creating the schematic, and then from the schematic, creating a PCB, and then from there, we'll export a Gerber file and then inspect the Gerber file to make sure that it is correct. So I'm sharing my screen once again. Right, so this is the circuit that we are going to be creating. It receives a 9-volt input. It's got a 555 timer with a connect to two resistors and a capacitor. So this is a polar capacitor, but it doesn't really matter. We can use whatever capacitor we want. And then we have a counter. So each time it receives a pulse, it will switch on one LED. So this is my counter, these are my resistors, and then these are my LEDs. So that is what we are going to be creating right now. So I'll be creating this circuit. And I'm just going to I'm just going to add in this exact circuit I'm going to be using. So we have the circuit. And now we have to create the schematic for the circuit, because most of these circuits that we find do not have the schematic. So we'll start doing that. Schematic, we first change our grid to millimeters. Now, once again, you do not need to change the grid to millimeters. It is just something that I like to do. I just like working millimeters. Inches don't make much sense to me. And I have a frame. Now we can also give the frame a value. Why are we doing this? Well, it's not that important, but now this is so we don't have the error of elements not having names. Okay, so right, we have our grid. What we need is a couple of resistors. So let's create the oscillating circuit first. So firstly, let's create the oscillating circuit, and then we'll move on to the counter circuit. So let's just have a connector. So I like the connector which I used previously. Where is it? Yep, it's a custom connector. And let's put that down there. Now I would like to have the power up top. So how can I do that? Let's mirror the component and then rotate. So I have my power at the top, my ground at the bottom. And now I need two resistors. So let's open up resistor. I like the US symbols. And I've decided let's have some SMD. So I'm going with SMD. on the M1406 package. Those are the resistors I like. Oh, no, let's go with this one. The M1206 package. So I have my SMD resistor. I need 2 of them. 1, 2, and then I need a capacitor. And also now let's go with the US signal. Let's see which capacitor. And let's also go with a surface mount capacitor. And I need a 555 timer. Now, this is quite tricky. If I search for 555 timer, I will have no results. If I search for 555, nothing. If I search for timer, it comes up with these, and there is my 555 timer. So, as we spoke about in the previous class, the search function that that Eagle has is terrible. You have to search for very specific things to find the specific components. If you have the specific component number, that is usually better than searching for the description. And a lot of the times it's easier just to make up your own custom definitions, custom components. But usually if you look long enough or if you browse through all the options, you will probably find it. So here we have a 555 timer. We can have it in a dual inline package. We can have a surface mount. So let's have a surface mount package. Right, so let's have surface mount. And we place it down. So now we can connect up our circuit. So we have a power circuit. The power circuit runs to, so these are, I have to explain this as well. Sometimes the ICs aren't numbered quite in the way you would expect. Now, the person who designed it might have a very good reason why they put the pins in such a way, but please have a very good look at the numbering of the pins and ensure that you're connecting the pins up to the correct elements. So let's have a look at what I mean by this. So this is my 555 timer, and here I have pin number 1, number 2, 3, 4, 5, 6, 7, and 8. Now, this is not how the IC usually works. The IC usually starts from 1, 2, 3, 4, 5, 6, 7, 8. But here the pins are also like scrambled, and also it is 1, 2, 3, 4, 5, 6, 7, 8. So just bear in mind that you connect to the correct elements. These are still number 1 is still number 1, 2, and so on. Just to make sure that you are connecting to the correct pins. So right, our power pin connects to this resistor, our input resistor, and then it also connects to pin number 4. Pin number 4, and also pin number 8, which is V+. Right. These two are connected. And this is now connected. My resistor is then connected to the capacitor, and then the capacitor is then connected to ground. Pin number 2 and number 6 are connected between the resistor and the and those connections. And pin number 1 is connected to ground. And then pin number 3 is outgoing, and pin number 5 is not connected. So this diagram is now connected in such a way like this. And this is where our diagram is going out. Now we have to name all of our components and give them values, right? So that we know what is going on. This is my 1K resistor. This is a 68K resistor. The capacitor is 3.3 microfarads. And the 555 timer obviously is a 555 timer. It does not need a value. Now, the next part of our circuit is the IC. The specific IC we're looking for is a 4017, and it is a counter. Now, we'll run into the same problem as with the 555 timer, being that this is not very easy to find. So let's search for 4017. Finds nothing. Let's search for counter. Aha, it finds some counter. This is the 4017 range, the one which we want. So we have these two counters. Here we have our surface mount package. So this is the one we are going to be using. This is my counter. I also now need a couple of resistors. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 resistors. So I can also see, okay, so I've used my, I click on this arrow and I can see which resistors I have used in the last short while. And these are the resistors I'm using, or I would like to use. Let's get back to my we'll have to so we are connecting up from 0 up until 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we can connect up these resistors. And please see that these These are the pin designations, so what they do, and these are the pin numbers. So 3, 2, 4, 7, 10, 1, 5. So they're all mixed up. Just make sure that you're connecting the correct pin to the correct component. And I see I'm missing an extra resistor. So let's just get another resistor. And connect that up as well. So I've now all got my resistors and they all are 100 ohms. So let's click on this and zoom in a little bit. I click on values and just add 100 for all of them. Right, and I also need LEDs. Okay, so let's look at our parts. Type in LED. And then Adafruit, got nice LEDs. So let's also have these. Let's have a look at what other LEDs we have. Pretty big surface mount LEDs. Now you will have to find the exact LED that you want. There are quite a number of LEDs. Let's say I would like this specific surface mount LED. Each one of them has their own LEDs. But let's try something crazy. And click on. No, that does not work. Right. Let's just have it as red. So this is quite tedious. I mean, we have to have everything named. Everything has a name and a value. And then we can connect everything up. Oh, that was a mistake. And then all of these LEDs are connected to ground. Now what I can do is, as with we can add in a ground node. Now let's have a look at GND. I have a ground node. And what I can do is I have a ground supply on this side. And I just connect these LEDs directly to ground. Oh, I don't think that's connected. Right, our other chip as well. So the clock is connected. I don't think that is connected. So let's delete these two elements and connect them up properly. Our enable and reset are both connected to ground. So let's have another ground connector here. And we have the number 10. Well, this pin not connected. Right. Just like we have our design here. This is more or less done. The only thing that we need to do is just add the VCC chip, because this still is our VCC chip. So it needs to have a VCC connection, because this IC, the VCC is here for us to use, and this is not. So we have to create a VCC. And once again, what is the VCC? It is just the supply power. So all of our hidden pins of the IC, see, that's not right. All of the hidden pins within the IC is then connected to VCC. So this is now connected to VCC as well. Now, the next step that we have to do is to name all of our nets. We can use the name function. Now, obviously, this should be VCC. This is also VCC. This is our DIS net. And this net is our threshold, TRHR. And this is our clock, CLK. Now, this will be R to D1, R to D2, R to D3, R to D4, R to D5, R to D6, R to D7, R to D8, and almost done, R to D9, and then R to D10. So this is just the net between the resistor and the corresponding diode. We also have to have this IC to R1. It's actually R3, isn't it? IC to, oh no, actually what? Better is if we name it Q0, Q1, Q2, Q3, Q4, Q5, Sorry, that is wrong. Q3, Q4, getting ahead of myself. Q5, 6, Q7, Q8, and Q9. Now, we should have all of our nets named. Now let's just check the ERC. Oh, and we have a couple of elements that's a bit of a problem. So first we have no supply from implicit power pin IC2P-VDD. Okay, so that's a problem. VSS. Unconnected pins 2. So we have got a couple of problems. So the problem is that some chips use VCC, some use VDD, and some use VSS. So we will have to change our pin designations just to solve all of those problems around. So let's, I'm going to share this again. Let's search for VDD. And there we have VDD. So we are going to be replacing our VDD, or this net with VDD. So now let's check our errors again. Aha, good. So the VDD is now saved. Now we don't have VSS. So what is VSS? Well, VSS in this terms should be actually our ground. So let's search and see if we have a VSS. And we actually do. So we have to replace our ground with VSS. Now, the only problems we are going to probably have from here is we have to delete all of our ground and replace them with VSS. Let's have a quick 5-minute break, and then we'll talk about VSS, VDD, and VCC and why that all makes a difference. So let's have a quick 5-minute break, and I'll see you guys in 5 minutes. Quickly try to find a good definition of the difference between VCC, VDD, VSS, and so on and so forth, and ground and all those kind of things. I didn't really find a very good definition. I did find some sort of a definition. Sharing my screen. VCC and VDD are both positive voltage sources. VEE and VSS usually negative voltage sources. VCC and VE used to with BJT, bipolar junction transistors, and VDD and VSS used with FETs, field effect transistors. So CC usually with collector, and DD usually with drain, emitter, and source. So what does that mean? Well, you have to be careful with these integrated circuits with hidden pins in Eagle. But the good thing is, always run the ERC, the electrical rules check, and then that will then tell you there is a mistake somewhere. So if there is, just make sure that you add a net of VDD or VCC or VSS or whatever it needs. Just connect those up as we have done now. So let's have a look and see if our errors are gone. Yes, and we also have one unconnected input there, which is fine. That's fine. That's something we can live with. And let's have a look and see the close but unconnected wires. That I believe is fine. Yeah, it's all, these are all just right, that is fine. Right, no, these are all approved. So we have created our little circuit. We can add in a little note. So a note, a little bit of text. And what do we write on our text? We usually have these in bullet points. And this is a flashing LED circuit using a 555 timer and a counter. I usually like to have it in the info. And we find a place where we can fit, and there we have it. So let's save this. Ask us what we want to save it as, and let's save it under the name. Let's save it as Night Rider. Right. So now we can have a look at the different elements which we can export. As I told you, you can export the net list, show me all of the nets, the part list, the pin list, the bill of materials, which gives you all of the materials that you are using, all the resistors, and so on and so forth. But we don't really need that because we're not going to be building a circuit. This is just as an example. So let's switch to board. It'll ask you, this board doesn't exist, created from the schematic, and I'd say to it, yes, please. Right, so now we have our little board created. First things, change my grid. I like millimeters. My alternate to millimeters, 0.1. And display my grid. Thank you very much. Now we can change our board outline. Now my board outline, what do I like it to look at or looks like? Let's create a dimension. And let's create a circle. Because why not? Everybody loves circles. So let's have a look at manufacturing. So we have a very good, nice circle. So our board then has these elements. So now we can start moving them into our device. So let's move in our, so once again, switching back to this, let's start from the left, working to the right. So we first start with our power in, with our power source. I need you to move. And let's leave you there. But first, let's create some design rules. Let's just review our design rules. Edit, design rules. And everything is relatively fine. I mean, I'm not going to change all these design rules. I don't have a specific design elements. So, and place it down like so. Now we are looking for resistor number 1. Resistor number 1. Resistor number 1 goes to resistor number 2. And then to the capacitor. Resistor number 2. Let's move you into our board. Once again, we can let's look at our info. We have a position, X, have our X position at 9. And also this resistor also have our X position at 9. They are nice and straightly aligned. Wait a minute. Let's move this like so. Now it goes from power through this. Then I'm looking for my capacitor. There is my capacitor. And place it down. And I can also now change its info to position number 9. And it's all nicely aligned. Next, I'm looking for my 555 timer, which is IC1. I want to move you. Now let's have it in this position here. From my 555 timer, I go to my IC2, and then from IC2, all of my resistors and all of my LEDs. Relatively simple, relatively straightforward, right? So let's have it placed here. And then resistor number 3. I have you placed here. And then LED number 1. Lost. LED number 1. I would like you there. And then we have resistor number 2, or resistor 4 in this case. Going to LED number 2. And then resistor number 5. To this LED. And you can see how this kind of works. So what my idea is, I've got this little round board, and then I have these elements inside of it. Resistor number 7. Have it up there. Resistor number 8. Let's have that there. Resistor number 9. I have you there. Resistor number 10. This is number 11. Right, and then my LEDs. I have you there. Let's just zoom in a little bit. Right. So now I have all my components on my board the way that I wanted. Now, it's not really exactly a very good design. I am aware of it, but it is my design and it's the one I'm sticking to. But we can, I just want to see what this does. I've got a straight line up to there. Right, that does not do anything. I'm just experimenting a little bit with my little board. And it does nothing. Good. So let's have a look at my board. Now you can see all of my components are on this board. So just for interest's sake, let's mirror these components. Now, I clicked on mirror, so remember what mirror does. It flips, mirror with inside of the board. It flips it to the other layer, and that is what we have done now. So I've flipped some SMD components to the other layer. So now this creates a little bit of a problem because we have a now we have to somehow create connections between the top and the bottom layers, and that is done via a via. Right, so we can create this. We can create our what we call our air wire. We can connect our circuit up. So we can start the top layer. This is a bit too thin for my liking. 0.2 is a little bit better. And this is also VDD. And these are connected. So VSS, I'm not going to be connecting quite yet, mainly because I'm going to be leaving that for the ground plate. So all the VSS connections, I'm going to be leaving I'm going to be leaving because I'm going to be using the copper fill to create a ground plate. So threshold is, let's connect it to here and then to there. Discharge, now we have to route a little bit more carefully to there. Threshold is connected to threshold there. 5 is unconnected, and we have to connect this to VDD. We'll create this connection up to VDD. This is also connected to VDD. VSS, and then we have our clock connection. Now, what I'm going to be doing is I'm going to be connecting all of my, now you can see in here are all my net names. I'm going to be connecting everything up and then using like that magical thing to straighten off all my lines. So that's VSS. Connect these. Now we have a little bit of a problem. So let's do these first. Connect these. Connect these. Let's say we've connected this up. Now, what is my problem? I have to connect this here to this pin. Now, luckily my line is small enough that it can pass through these and connect it there. Now I will have to place a via for these connections. So let's create this connection. I create a via, and then so what did I just do? I started routing from the one layer. Let's do that again. I routed from the one layer. I then placed down a via. And then this is now connected on the one layer to the via. I then switch to the other layer and then route this to the layer that I want. So this is a hole going from the one layer to the other layer. I can do the exact same thing, or I have to do the exact same thing for this connection. I click on via, place my via at the end of the wire, switch my layers, and connect that. I can connect these up as well. No, just to there. Now I also need to connect the ground connection, or VSS, of the bottom layer. But what I am going to be doing rather is creating a polygon on the top layer. And call it VS, oops, not VCC, VSS. If I click on Rat's Nest, now you will see all the VSS connections are connected to my copper full layer. Now what I can do is I add a via. And then I do the exact same thing for the bottom layer as well. Let's have the bottom layer. And have VSS. Click on Rat's Nest. And I can see now the VSS is also connected. So what did I do now? So a via is basically a conductive metal filled hole connecting your layers. So if I have components that are only connected on one layer, like a surface mount component, if I have components on another layer, then I will have to use a via. So I can route on the one layer to a certain point, create a via, and then that via then connects to the bottom layer, and then I can route to that component there, creating the connection. Now, what I did was I created a copper full region for the top layer and called it VSS, or my ground layer. It then connected all of the pins called VSS, or connected to the VSS layer, onto this copper full mass. I then added a via onto this copper full mass, which basically created a connection from the top layer to the bottom layer to the net VSS. And then I created a copper layer at the bottom connecting VSS. So the top layer and the bottom layers are all connected. If I click on manufacturing, I can see my connections there. Now I do have one connection still left over. I just want to see if my tools, ERC, that is everything fine. Let's have a look at my errors. It tells me I have one air wire, meaning that I have to route one element. And I believe this element now I have to route, I think it's on the bottom layer, from this component to this component. Just want to see if that actually worked. Right, so everything is connected. We usually just add in this, sorry, you're looking at me doing, I didn't share my screen. We usually add in the copper fill layers right at the end. Because it fills up all my layers like this. So we have everything designed as we like, which is perfect. Now, the next element that we can do is we can export. We can click on CAM processor. And we have to save the design. Yes, perfect. We have our Gerber files. Right, process job. Where do we want to save it? Let's save it in this one, and we create a new folder for our night LED, for instance. All of our Gerber files now saved in here. So let's see what they look like. Online Gerber viewer. I'm just opening it up. It sometimes takes a little while. Let's look at my Gerber files. Export night light. It is not there. That is very, very bad. Let's have a look. New folder, cam outputs. It didn't save where I wanted it to save. That is fine. It's saved as in the new folder. That is fine. We'll just open that up. Go to files, select all of them, open it up. And here I have my top and bottom layers. And you can see everything is connected, top and bottom, with my vias. And that is that. So as well, the website I'm using for this, for the Gerber file viewer, it is actually also a PCB manufacturing company. So a lot of these PCB manufacturing companies would offer you a service like this, where they would have, where you can upload your design files, check your design files. Once the design files looks fine, then you can download it or upload it on, or order your PCB. I'm sharing my screen once again. And remember, we had a, let's just have a look at the Gerber files. Remember in the option where we only used through-hole components, our solder paste elements was empty. Now we have solder paste top and solder paste bottom. Now, as we spoke about, oh, sorry, we've got a question. I see a hand up for a question. Do you have the question, or was that just a mistake? I see a hand raised. I was wondering if that was a question or just a mistake. Just lower your hand. Right. If there are any questions, just raise a hand like you just did. But then if I ask you what's the question, just react or type in the chat or something what the question is. So the point I'm trying to make is that you, in the design where we only used through-hole components, we have no solder paste. And now when we are dealing with SMD or surface mount devices or components, we also have the option to add in solder paste. So as we spoke about this in the previous class, the solder paste map, our manufacturer can also add solder paste for us. So on the pads where our surface mount components are located, it will place down solder paste. So the only thing that we need to do is then just put when we receive the board, the solder paste is already on there. So we only have to put down our SMD components at the correct position, apply heat, either through a heat gun or a soldering iron, and our component useful thing put on the solder paste. But also if you have somebody who assembles your circuits for you, solder paste locations, and Yes. That is also another reason why if you have mass manufactured circuits like you have in your mobile phone, a lot of the components, surface mount components, are generally a lot smaller, sometimes cheaper as well. Well, mostly they are cheaper. But one of the big benefits is that you can have a machine place the component and then solder it. So what happens is you would have what we call a pick and place machine. It will receive the board with the solder paste on it, which your manufacturer did for you. You'll put the board down. It'll look at or reference the solder paste mask or the solder paste layer, and then place the correct component at the correct coordinates. And then it'll apply heat, usually through a heat gun, so sort of like a big blow dryer, which would then melt the soldering paste, creating the connection. So that is a huge advantage because you can have a machine or something automated that makes your PCB, the physical PCB, attaches the solder paste, and then attach a component to that solder paste. Now, machines can do through-hole components. That is entirely possible, but it takes a little bit longer because the wires have to be bent and inserted exactly into the holes. We also do that, but surface mount components are a lot easier for mass manufacturing. That is why for most consumer electronics, you will have mostly surface mount components most of the time. And that is why we have the solder paste top and bottom parts of those elements. So if I want to have this manufactured, I would create my Gerber file, click on CAM, C-A-M, create the Gerber file, and then upload it just like you have just seen me do, and then send it away. Usually the company will then come back to you and tell you or give you a summary of the board, how much it's going to cost, what it's supposed to be, what it's supposed to look like, and then send all of this back for you. And that is basically it for a very, very simple circuit design. Now, I did play around a little bit with the circuit design where I created a flashing light circuit with in a circular design. You can have any shape you want, just bearing in mind that most of the time your circuit has to fit in somewhere or be somewhere. We also used, well, we didn't use different size SMDs this time. We stuck with one type SMD. Right, so this is the end of this specific class. Today was a little bit there was confusion about the first class and some people didn't get the link. I apologize for that. I will now create the links for the classes of next week and send them to you straight after this class is finished. So we should have classes on Monday, Wednesday, and then on Thursday. So when you receive the links, please make sure the classes are correct. And if they are not correct, just send me a message and then I will try and we'll try and make a difference. So next week as well, what we will be doing is we'll be looking at creating custom components. So a lot of the times, as you see, I struggle, or there is a struggle finding the correct components in Eagle. You'll have to know exactly what you are searching for and under what series number the component lies, i.e. is it a 74 type TTL transistor type device or technology. And a lot of times it is easier to create your own components. And we will be creating that on Monday, where we will create custom schematic or the custom symbols to be used in the schematic view. And then also this custom footprint, where we will be creating the footprint. So we'll look at a data sheet of a component and then create that component in a custom way, and then use that in a PCB design. Also, next week, we will be looking at or creating more complex PCB designs, but it doesn't really, we will increase the difficulty, but the difficulty does not increase exponentially. If you have a good grasp on how to create a simple PCB, either routing tools, then more components does not really make a difference. And a lot of the times, if you have problems, use the auto router, and the auto router can route your components for you. We also look at next week, so like the difference between auto routing and routing it yourself, or letting the auto router do some work and then you complete the work after that. But just remember, the auto router, all that it does is it has mathematical function. It's an algorithm that runs mathematically, connecting all the points. It does not really care about electrical rules or how nice and neat the board is. It just cares about connecting your board in as much efficient and continuous way possible. Right. So this was today's class where we continued looking into PCBs. I'll end this class right here. I hope you all have a wonderful day, a wonderful weekend, and then we'll look forward to the last week of class, which is going to be Monday, Wednesday, and then Thursday.